Welcome back. This is the Tutor Wizard. I'm Adrian. Please subscribe right here and hit the notification bell, apparently. That will give you notifications for this series and a bunch of other ones on our channel. If you're doing multivariable calculus, I'm assuming at least one other thing might be all right on our channel. We're doing Chapter 1, Partial Derivatives. Section 1.5 is the chain rule of functions of more than one variable. This lecture, what we're going to do is what most of the books are going to call the general chain rule, where we'll explain it in a second, but now we're going to have a function w, say, and it's going to be a function of n variables x1 to xn. If n is larger than 26, I run out of alphabet letters to call those guys, and then I need more for the other ones. So with w is a function of n variables, and then each of those variables inside there is a function of m variables t1 to tm, and we got a whole bunch of double indexing and all kinds of things going on. How do we take the derivative of that thing with respect to who and what's going on? The general chain rule and some examples. All right, so this is the general chain rule. What we mean by that is now we're going to do the most general scenario of w is now a function of n variables x1 to xn, and each of those variables is a function of m variables t1 to tm. Again, for ours, usually it's going to be 2 and 3 variables, or 2 or 3 variables. So the n and the m are usually going to be 2 or 3, not much higher than that. So it won't get too crazy. But it does get crazy. Look at that hot mess. Now what are we saying? If w is a differentiable function of these variables, and technically speaking, it should say of, not even with respect to, not the partials, of. So w is a differentiable function of the first ones, and these x1 to xn are all differentiable functions of these ones, variables. Then w is also a differentiable function of the second set of variables, and by the chain rule, or the general chain rule, we have that the ith partial of w with respect to the partial ti is going to be now this sum. We could also write it as this guy, but I'll spare you. And in Einstein's notation, we drop the I equals 1 to n and just know that we've been summing these. So we won't do that. But here what we have is, in each one of these terms, we're going to have the partial of w with respect to one of the first variables. And that means we're going to end up getting n terms. There was also, if you're keeping track of, I'm just giving you a quick rundown of how many of these partial derivatives you're going to have to compute. In how many partial derivatives do we have to compute? First of all, we have to compute m partials of w with respect to the second set of variables. In each of those partials we have to compute, here's one of them, or the general one, the ith one. In there we're going to have m terms. And in each term we'll have 2 derivatives that we're going to have to compute. These ones will get repeated in each derivative though. Let's do an example of this for a function of 3 variables. Example 1. W is a function of 3 variables, x, y, z, and each of those guys now is a function of 3 variables. So I've ramped it up already from the general. We've got now 3 and 3. I'm not going to make you compute all 3 of them, but for you, just for, okay, I guess, if that's not, is that the word you wanted? For practice, or for fun, you try to compute the partial of w with respect to r and t. We're going to do s for fun. I'm going to have fun. What do we need to do that? First of all, I'm going to take that hot mess that you just saw in the previous scene and now magically reiterate it for myself for the 3 variables I have. t1, t2, t3 now becomes r and s and t, and x1, x2, x3 becomes x, y, z. When I only have 3, I don't need this horrible indexing. So what does this say for us? The chain rule says the partial of w with respect to s is, I'm only going to compute 1, but we would have 3 of them that we would have to compute in general. In each of those, there's also going to be 3 terms because there's x, y, z. And in each term, there will be the partial of w with respect to x, for instance, and then x with respect to our variable. So this is going to give me the partial of z with respect to my first variable x, and then my first variable x with respect to s, plus the partial of z with respect to my second variable y, times the second variable y with respect to, no, where are you going? Baby one, s, plus the partial derivative of w, z got in there, Pavlovian. You'll do it too. I'm so used to working with functions of 2 variables, now you have to step it up. W, from now on it doesn't change as W. They should have kept it W and not used Z. From day 1 they should say W is f of x, and then it'll be W all the way up when I grow. And then I add Y's. Yeah. I'm going to rewrite all the books. Probably not. The partial of W with respect to our last variable Z times the partial of Z. I already did write books, but no one wants to read them. dz ds. This is, I'm reiterating the general theorem for what I now had. I'm computing one of the partials, dw, with respect to my first variable s, that I have an r and a t. But I also now know that to do that, I have to compute 3 terms, and I have to compute, in this case, I don't get to save myself any time because I didn't get to double up. The time save would be when I compute these, but I have to compute all 6 of these to compute our partial derivative. Now we're going to have to be doing some erasey stuff, because now let's get to it and compute all of these things before I mix it all up and give us one expression. The partial of W, first of all, I do, in my mind, I'm going to do these ones first, because those are focusing on W now. And then I will do these ones after, in my mind, to categorize how I'm going to actually compute things, because then that deals with these guys. Oh, if I was geometrically doing that completely, that was a... That should be a circle, shouldn't it? Yeah. You're like, are you actually going to do that? Yes, I am. Yes, I am. And you have to watch, because I got the microphone. There. Now I'm going to compute those 3 things first, focusing on W, and these 3 things second, focusing on X and Y and T as functions of R and S and T, or X and Y and Z as functions of R and S and T. Words, let's compute now. The first one is dw dx is equal to the derivative of this with respect to x, which is luckily going to give me, yes, y cubed. Remember, eventually we have to put what those things are and cube it, but I'll just leave it and don't simplify, just like on exams. Then the partial of w with respect to y is going to be a little bit nastier. This is going to be, by a little bit I mean a lot of bit in math, 3xy squared plus 2yz cubed. And then the partial of w with respect to z is going to be gone, and then I'm going to get 3y squared z squared. Good, that's what I'm saying. Now I've focused on w. Now what I have to do is compute partials of those guys with respect to s and put it all together, multiplying it using the chain rule. Let's do that. Let's recap. What have I done? I have moved everything up. What I did was I computed the partial derivatives of x and y and z with respect to our variable s now. That's those guys. Watch the previous videos, practice partial derivatives. Why do you think we want them for the rest of this chapter and the rest of the course and the rest of our lives? Then what I did also is I replaced the x, y's, and z's in the partials of w with respect to the x, y, z with the r's and s's and t's. Then after I've done that, it's the forest for the trees. You're like, good, I'm done. It's like you've got all the pieces now, but now you have to remember what they actually asked me in the question originally and go do that. So after I have all the pieces, now we're going to put it in the pot and make some soup. Nourishing. This is the partial derivative of w with respect to s. We have 3 terms because there was 3 x, y, z, 3 variables of w. Each term is going to have 2 partial derivatives. We've now computed all 6 of those partial derivatives we need. And the partial derivative of w with respect to s as a function of r, s, and t is equal to dw dx, this one, rs squared e to the negative t cubed. Yeah, I'm not simplifying. You can do that for fun after this when I'm done. Times this one, the blue one, r e to the t plus this one, whoa, 3rs e to the t times rs squared e to the negative t times 2. Put that in there if you want. Plus, we're going to need a bracket, 2rs squared e to the negative r squared s times sine t cubed, apparently, times what? The blue one, 2rs e to the negative t plus we're going to run out of board space. This is what happens when you do multivariable calculus, ... Then we're just going to keep going onto the wall eventually. Then plus our last term, this one, 3rs squared e to the negative t, or s squared sine t squared, times this guy. Don't forget one or I'll punish you thoroughly. No, okay. Close enough. Whew. What was that? Partial derivatives. Now let's take the second partial derivative. We're using a chain rule. Oh, that's crazy. This is the partial derivative we were looking for as a function of s and r and t. Next. All right, as promised, you're like, I didn't agree. I didn't want you to promise anything. Please stop doing it. As promised, we're going to do not only the first derivative, partial derivative, using the chain rule, we're going to then apply that, and because that, when we take that, that function is now still a function of all those variables, so we could take the derivative again. That's going to be the second derivative. Then you have to use the chain rule and Clairaut's theorem and clean everything up. And what is going on? Multivariable calculus. What do I need first? The first one I can do, then we'll think about what's going to happen, about what's about to happen to this. That one's going to be the partial with respect to r of the thing we already computed. That's what's going to happen. For now, 1, the partial of z with respect to r. My first function, I think to myself, is a function of 2 variables. Then these functions are both functions of 2 variables. That means this is going to be the partial of z with respect to x, and then the partial of x with respect to r, plus the partial of z with respect to the second variable y, times the partial of, not j, the partial of y with respect to the variable r. This is what we want to compute. Now I do that because I can't find these guys explicitly. What we're going to do is, that's why it tells us in here, they're trying to say you have to leave those in there and simplify and use your theory and Clairaut's theorem and simplification of what the notation of these partial derivatives is, and keep track of that. What they're saying is you're going to have to leave those guys in the expression. Their continuous partial derivatives exist, and we do have these explicitly as functions of r and s, so we can compute those. So to compute those, the partial derivative of x with respect to r, I don't have to do the s ones, is going to be 2r, and the partial derivative of y with respect to r is going to be 2s. I can put those in there. This means that the partial derivative of z with respect to r is equal to the partial derivative of z with respect to x times 2r, plus the partial derivative of z with respect to y times 2s. This is the first derivative. Check. Now we want to do this one. Let's see what happens. Now to compute this, the second derivative of z with respect to r is equal to, by using our definition of higher order partial derivatives, that's actually dz dr is a function of r and s, so that is the partial derivative of r with respect to the first thing that we just computed. But we have that now, and this is why we do things. Equals means equals. I can now substitute this anywhere this appears in another equation. So I'm going to put that in there, and then you simplify and use Clairaut's theorem and a bunch of other things. Modus ponens, this is all we have as a tool. This implies this. In Latin is modus ponens, essentially. We only have one tool. Keep using them. I'm going to use this and plug it in here. This is equal to the partial derivative with respect to r of this guy. The partial derivative of z with respect to x times 2r, plus the partial derivative of z with respect to y times 2s. This one's going to have to use the product rule because these are both functions of r. This one, luckily, he's held as a constant, so we won't have to actually use product rule there. So how many terms are we going to get? 3 terms. Let's do that. We have to move everything up. We had this hot mess. By using the product rule of this one, he's a function of r and s, and so is this one. So what we have is we take the partial with respect to r, we get the product rule here, and then this one was a function of just s, so we didn't have to do it, and we get this expression. Now what we have to do is, what are these guys? We have to use the chain rule again, and it's really hard to see. But this guy and this guy, the partial of z with respect to x is a function of x and y. Say w x y. And now I want to take his derivative with respect to r again. So if I was going to take the derivative of w with respect to r, and remember x is a function of r and s, and y is a function of r and s. Now, it's really hard to see at first, but this thing, or I'm doing this one first, this one is a function of x and y. Call it w. And so now this is this scenario. Get rid of that hot mess and just call him w. Now I'm taking the partial of w with respect to r, and w is a function of two variables, x and y. So there should be two terms, one for x and one for y. And then I take the partials, and then each term should have two terms because I'm going to split the mixed partial derivatives in the chain rule formula. So that's going to give me the partial of w with respect to x times the partial of x with respect to r plus the partial of w with respect to y times the partial of y with respect to r. Can you see the orange? I don't know. I need red anyways. I was going to use orange for something else and it changed because I guess I might as well explain that in the videos explaining things. Seems reasonable. Now do you see? W is this hot messy guy. So w is in fact dz dx dz dx. So that's why this turned into that thing. This guy is a function of x and y. So to take the derivative with respect to r, the inside variables, I first take the derivative of this guy with respect to the first variable, x. Then I take the partial of x with respect to r. Then plus the partial of that guy, the troublemaker, with respect to y, and then dy dr. And that's why we get this formula by the chain rule again. It gets a little bit more exciting too. Then we do it again. Same thing. This one is the inside. Now that I fix that, when I want to take the partial derivative over with respect to r, I'm going to get that thing with respect to x, and then dx dr. And then whatever you have inside there, that horrible thing, is going to be multiplied by the partial derivative with respect to the second variable, y, times dy dr. I know that's a lot of wording. Did I explain it very well? I know that this notation can become extremely confusing at first, so I'm trying to add clarity. I may have removed it slightly. Watch the video again, pause it, and think about it. This is what's really happening in there. We're just lazy. Now that I've used the chain rule again on these two expressions, I'm going to plug them in there. And what's the best part about this? What do I know about this one and this one? That is that guy. And that by Clairaut is equal to the partial of z with respect to y and then, or x and then y. So these mixed partials are equal to each other, so I can combine that term and simplify by Clairaut's theorem in a second. Let's plug those guys in there and then see what happens. From here now, we're going to write it out one more time anyways, but I'm plugging the light blue into light blue and dark blue into dark blue squares because we figured out what those are explicitly. Then we're going to use Clairaut's theorem to make those things equal to each other and simplify and then write out the final hot mess of what this second order partial derivative is of z with respect to r twice. This is going to give us that guy is equal to the blue one. So now I get the partial, I'm plugging this in here now. I get the partial squared of z with respect to x squared times dx dr. Then I have plus the partial squared of z dy dx, which is equal to this one also. And that one is multiplied by the partial of y with respect to r. And then I have plus 2 times the partial of z with respect to x, that guy. Then I have plus, remember we already calculated him in part 1, don't forget, oh, we're going to have to put him in there too, just a second. And then the blue one is what? I have to squeeze that in there also. This is now the blue one. I have the partial of z squared with respect to dx dy times the partial of x with respect to r plus the partial squared of z dy squared times dy dr. Now I plugged these two things into here. Now what I have to do is use Clairaut's theorem and clean everything up and substitute what everybody is. Let's do that now. This is going to equal something that's going to make me run off of the board, most likely. Here now I have the partial of z with respect to x squared times the partial of x with respect to r. Remember, can we remember what it was? Is that what it was? I don't remember. Go back. Yes. Pythagorean triples. What? So, what this is 2r is what I'm trying to remember. dx dr is 2r. Plus, now this one, d squared z dx dy. Yes, you're like, you flipped it. Yeah, I'm allowed by Clairaut's. That one is times dy dr, which is 2s, plus this one, which is dx dr, which is 2r. So I'm combining this term and this term right now in my head. These two guys are equal by Clairaut's, and so I can factor those out, and then dy dr is 2s and dx dr is 2r. So that's taking care of those two terms, this term, and plus 2 times what was dz dx. We leave in there, sorry. And then here I was cleaning up, this one is plus the partial of z squared dy squared times dy dr, which is 2s again. All right, so in between there, I made a mistake somewhere, so I had to catch it. So we were at this stage. I think I forgot the 2r and the 2s for some reason when I moved it from here to here. This is what we're having to compute now, and we had to compute these things explicitly. I put those in there. Once I put those in there and simplify, I should have 2r times this one plus one of these guys. Anyways, simplifying, I got it right this time. If you expand out, remember we had expressions for this one and this one. We plug them in there. Then I simplify everything out. I also noticed that now by Clairaut's theorem, these two guys are equal, and that's why we get 8rs, this guy, from this stage now. So putting that in there and not forgetting the 2r this time, when you put that in there, remember there's two terms in here, and there's two terms in here. Foiling that all out and simplifying, I get this. These two guys are equal by Clairaut's theorem, so they become this one term, and I get 2r times, or this term first of all, we get 2 dz dx, and then this term is 2r times 2r is 4r squared times the second order partial derivative of z with respect to x. Then we combine these two terms to get 8rs times the mixed partial derivatives, and then we get 2s times 2s is 4s squared times the second order derivative with respect to y. I think we got it there. What that says is the second derivative of z with respect to r is equal to 2 times the first partial derivative of z with respect to x plus 4r squared, partial derivative of z squared times x plus 4s squared partial z partial y squared plus 8rs mixed partial derivatives, which are equal by Clairaut's. This is the second order derivative. Don't try this at home. Yeah, no, specifically try this at home, kids, but you're going to have to try it more than once. I did. There's a bunch of moving parts. Practice, practice, practice. Let's do another one. That was only like 2 minutes in the video, but that took us a long time behind the scenes. All right, that's how you know you like math. That last one was quite the doozy, but let's do one more. I want to talk about the tree diagram. So what's a tree diagram and what does it have to do with the chain rule? What we're going to do is they give us a function of 4 variables, 3 spatial coordinates and a time variable, or x, y, z, t. And then each of those coordinates depends on 3 other variables, u, v, and w. So we have a function r, which is a function of 4 variables, and we have each of those 4 functions are functions of 3 variables themselves each. And we want an expression for the partial derivative of r with respect to the first variable inside each of x, y, z, and t. To do that, a good way, or whenever they ask you for this and counting how many total partial derivatives we're going to have to compute to find all the expressions for the original function with respect to our variables, is using a tree diagram. So what I do is, to simplify, I'm just going to use the variables, or you can write the mixed partials in there. Maybe we can write the mixed partials. So if I have r depends on 4 variables. Which ones? X and y and z and t. And now, the reason I spread those out more is because they all now depend on 3 variables. So x and y are awfully close to each other. Do that one more time. It's not surgical. Math is experimental. They're a little bit further apart now. That seems to be roughly equidistant. I like it. Now I have 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. And then what do we have? U, V, W, U, V, W. Now what that says is, if I want to compute the partial derivative of r with respect to u, how can I use this tree now to keep track of, first of all, and then we can count after if you really want as well. I want to, so we're probably going to. I want to compute the partial derivative of r with respect to u. I can squeeze it in right here. First of all, I'm going to have 4 terms. Why? Because I had 4 variables originally. And then we're going to take the partial derivative of r with respect to them, and then them with respect to these guys. In this case, we're doing u. So this is going to be the partial derivative of r with respect to the first variable x, or dr dx, says the tree. And then times what? Dx du. What does that say? That says these guys came from this scenario. Now you can see where I'm going to go with that. Plus I'm going to get 3 more terms. Now we're going to have plus dr dy times dy du was the one I was looking for. And that one says these 2 terms are coming from here and here. And then the next one, I'm going to have dr dz and dz du. Where do those ones go? The green ones are now going to be this one and this one. This is where I'm getting them from the tree, so you can keep track of this. Remember, if there's a whole bunch and you have 15 variables and then 12 variables, it's like, whoa, what's going on? Yeah, compute all of those things. And then the last one we need is, sorry, Blue, you're on the next line. It's all right. Then we're going to get the partial of r with respect to our final variable t, and then dt du. And that's going to say that those ones came from here. And then now that keeps track of the partial derivative that I need of r with respect to u. Counting for a second now, what does that say? In general, how many derivatives of r with respect to the variables of these things could I compute for this example? This function had 4 variables, so I'm going to call that, say, n equals 4. xn, it's n variables, it's 4 variables. And then we said in general, these guys could be t1 to t2, blah, 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 blah. That says m now is 3, t1 to t3. There's uvw, they've called them. And x1 to x4 is xyzt. Now, in that scenario, how many partial derivatives of r with respect to the variables will I have to compute? First of all, there should be 3 of them. You could compute the partial of r with respect to the variable u, the partial of r with respect to the variable v, and the partial of r with respect to the variable w. That's omega. The other ones are w's. Why? Omega is curly, w is rectilinear. Now, so there's 3 of them. In each of those guys that I have to compute, how many derivatives are there I have to compute? I'm going to have 4 terms. And then in each term there will be 2 products. Why? Because there will be dr dx and then dx du, for instance. And this is how you can keep track of how many partial derivatives you would have to compute if it says compute them all. And then in each of those partial derivatives, how many terms am I going to have for the number of the first variables? And then in each term, you have to compute those two partial derivatives, dr dx, dx du, dr dy, dy du, dr dz, dz du, dr dt, dt du. Let's be pirates. Please subscribe right here and hit the notification bell. I'll see you next time. I've had enough. No, never enough. One day you're gonna be able to grab it with your hand and just be like, get on the page there. When does that happen? Hurry up, technology. Or slow down. I don't want to be the chimpanzee in the scenario of me and AI. What? Never mind, human.